So motors are one of the most difficult topics, I feel, at GCSE physics, because they use a lot of A-level physics without really explaining it in too much detail. So we're going to go into the basics first, about a bit about magnetism and electric currents and how they affect each other. And to think about that, we need to go back to EM induction. Now remember, in EM induction, we were creating electricity by moving a magnet inside a coil of wire. So I've got a little triangle here. It's kind of like the triangles we use for equations, but slightly different. Okay, so if I cover at one side, I can make it if I have the other two. So to make electricity, I have to have magnetism that is moving. So I move a magnet. I put wires in the middle because you can't just make them appear. They have to always be around. Now this works in other ways as well. If I want to make a magnet, I can make a moving electrical current. If I move, electrical currents are by definition moving electrons, so I get a magnetic field whenever there's an electric current around. And if I want to make movement, I can use electricity and magnetism together to produce that. And we're going to look at how those work today. So the first thing to look at is this. This is a current carrying wire. Okay, I've drawn it twice and I've drawn one over here, and it'll become apparent in a moment. But the arrow indicates the way the electricity is going. Now, if you put a magnet near a coil of wire, the magnet will no longer point north. Say this is north. The magnet will align itself to point with the way the electric current is going, because this current carrying wire produces its own electric field. Not electric field, sorry, it produces its own magnetic field, which messes with this compass and causes the compass to align with the magnetic field caused by the wire, not by the magnetic field caused by the earth. So it no longer points to north. Now if you put lots of them around a wire, you get the magnetic field pattern. And the pattern that you get looks something, well, it doesn't look something like, it looks like concentric circles around the wire. So here's my current carrying wire. The current is carrying this way, and the magnetic field travels so that a free north pole would go that way around the wire. Okay, so any current carrying wire has a magnetic field around it, and that magnetic field is really useful in the motor effect. Okay, now this is here, we're producing magnetic field because we've got an electric current that is moving, it's moving electrons, so we're doing these two, so we're producing magnetism. The opposite can happen. We can use magnetism and electricity to create movement, and that's what we see in the kicking wire experiment. Okay, so here I've got a setup. I've got a north pole and a south pole, so here between these two there is a magnetic field. And we draw it like this because it's the way a free north pole would go. We draw it like that. Okay. Now let's imagine that our wire is carrying an electric current, and the electric current is going this way. It's coming downwards. Okay. Now if we attach this to a battery or a power source, so let's draw. I'm going to draw a battery quickly here, and we put it into this magnetic field, we see that this wire would kick. It would kick upwards. We'd see it flick. Okay. Now the way that it would kick, the direction it would kick, depends on Fleming's left-hand rule. Okay, so Fleming came up with this idea, well, not came up with the idea, came up with a rule that described what way this wire would move. So this wire actually moves. You see it move out of the page if you looked at it in real life. There's lots of videos about this, I'm sure, as well, but it's something you might have seen in your physics lessons. Now Fleming's left-hand rule requires you to put your hand like this. Okay, so it's a kind of, I can't really describe the shape, but you have your thumb, your finger and your second finger all at right angles to each other, and this is my really bad drawing of it here. Okay, there's a right hand rule, which is this one, and there's a left hand rule, which is with the left hand. Now the left hand rule is the one we need to use for this experiment. Now the thumb, TH, the thumb shows the direction of the thrust or motion. Okay, the first finger, F, shows the direction of the magnetic field, and the second finger with the C in it, second, shows the direction of the current. So if I kind of show that here, we've got my first finger is the direction of the field, the current's going downward, and that shows that the kick must be upwards out of the page. So if I've got magnetism and electricity, I will get motion. So this is magnetism and electric current, it will cause a motion to occur. Now this is the basis of a motor. Okay, but a motor is a little bit more difficult, and it's one of those ones where I'm going to try and explain it, and it might not be the best explanation, but hopefully it will give an idea of what's going on. So I've got here, once again, a magnetic field going from north to south. I'm going to just quickly draw my field lines and dash them in. So there's a magnetic field here between the two poles of those magnets. Okay. Now I've got, you can see a coil or a loop of wire. Okay. Now the loop of wire has it with the electricity is travelling in this direction. Let me get my pen out. In this direction. It might not match with what I've drawn here. So it travels along there, down here, and up. Now, I've just worked out that if I look back to my kicking wire experiment, quickly come back to here. When electric current runs this way through this situation, it kicks upwards. Okay, and we can see that happening here. So on this side, we get some upwards motion. Okay, so this part of the coil moves this way. Now here we can see that the wire's going in opposite, the current's going in an opposite way. So if I use my left-hand rule, this is where it gets tricky. My first is the field, my second is the current, and we can see that the motion thumb is going downwards. So this bit is going to go downwards into the page. So we get that this loop is spinning like this. Okay, now this loop can do a complete turn. Now when it's in a complete turn, it's going to do something funny, because then we're going to have a current going this way and a current going that way, so it would switch back. So you'd expect this weird motion of the loop doing this and this. That doesn't happen. The loop spins round and round and round and round, and that's because of these things here. Okay, now this is called a commutator and a split ring, and it's got brushes. These things are split ring commutators, and here, these bits, I'm not really drawing them very well, these are brushes. So let me write that down, that's a brush, and this is a split ring. I always spell this wrong, commutator. Okay. Now the brushes mean that these aren't actually attached, they're just brushing past. They're just brushing past like this, so they're not actually attached. And the split ring means that these two halves aren't attached to each other. Now once it gets to this point, it's flipped around. Because these connections have changed and switched again, all that happens is the current is once again like this, so it keeps on flipping. So the split ring commutator and the brushes mean that this motion is a continuous looping motion, not a weird jerky backwards and forwards motion. And this all happens because of this kicking wire idea and Fleming's left-hand rule. So we've got electricity causing motion because of the magnetic field, and the left-hand rule means that we get this rotation. The split ring means that rotation carries on and on and on. And that's the basic principle of a motor. If this is then attached to something else, if you have a axle through here, and you attach this axle to, say, a wheel, that's an electric wheel, or a motor that's attached to an electric motor that's attached to a wheel. And it causes that wheel to spin, which is obviously a really useful motion in everyday life. It's not the most detailed description of a motor, but it's one that should hopefully get you through GCSE. And hopefully it's simple enough to understand. But just remember that it's a kicking wire experiment, Fleming's left-hand rule, and it's these split rings and brushes that allow that motion to carry on being a loop, not to jerk backwards and forwards.